Hello, everybody. I'm Carlos Koenig, the president of the IMU. I have received the following introduction for Igor Krichever from Nalini Joshi, Sydney University, Australia. I am honored to introduce Igor Krichever from Columbia University and Skoltech, whose work has had an enormous impact on the theory of integrable systems due to his profound insights in geometry. These range from elliptic cohomology, where he proved the rigidity of important genera that bear his name, to the algebraic geometry of moduli spaces of curves. He found algebro-geometric solutions of soliton equations, in particular the Kadomstedt-Petyaschvili equation, using what is now known as the Krichever construction. He made key and decisive contributions to the solution of the Schottky problem, Schottky type characterization problems for Jacobian prime varieties, culminating in his proof of the Welter's trisecant conjecture. Through Krichever's very influential work on Witten type averaging of perturbations of integrable equations, real normalized differentials became a powerful tool in complex algebraic geometry, leading in particular to the resolution of Arborello's conjecture concerning compact subvarieties in the moduli spaces of curves. So it is an extraordinary pleasure for me to invite Igor to present his plenary lecture on algebraic geometric methods in the theory of integrable systems and Riemann's Schottky type problems. Igor, please go ahead.
Thank you. Thank you, Carlos and Nalini, for introduction. Even more thanks for you and other organizers for your efforts to make this extraordinary meeting happen. I'm happy to speak today. Let me just share my screen. Can you see it? Okay. I will speak today on algebraic geometrical methods in the theory of integrable systems and Riemann-Schottky type problems. The main goal of the talk is to present a certain circle of ideas and constructions of algebraic geometrical integration theory, which play a key role in the proof of the Welter's conjecture, which is the strongest known characteristic of Jacobians among indecomposable, principally polarized abelian varieties. This characterization problem is the famous Riemann-Schottky problem. The history of the problem is very long, going back to works of Abel, Jacobi, and Riemann. Despite efforts of generations of mathematicians, it had remained unsolved for more than 100 years. The approach to the proof of Welter's conjecture is applicable to a variety of Riemann-Schottky type problems. It was used for the characterization of principally polarized abelian prime varieties. The latter problem is almost as old and famous as the Riemann-Schottky problem, but is much harder. At the end of my talk, I will present the most recent result in this direction, the characterization of Jacobians of curves with involution. The problem by itself is pure algebraic geometrical, but was motivated by problems in the theory of integrable systems with symmetries. Application of algebraic geometrical integration theory to classical problems in pure algebraic geometry, I see as a kind of payback to the source of inspiration, because method of algebraic geometry lay in foundation of algebraic geometrical integration theory, whose purpose was completely different: solve certain nonlinear equations of mathematical physics. Let me start presenting the first player of the game, the Riemann-Schottky problem. And then I turn to the theory of integrable systems and the way I see it. Let H be the space of symmetric matrices with positive defined imaginary part, called the Ziegler upper half space. A matrix from H defines principally polarized abelian variety as a factor space of complex G-dimensional space by the lattice spanned by the basis vectors EI of the space and the column vector BI of the matrix. It defines also the Riemann theta function, which is holomorphic and lambda quasi-periodic. Lambda quasi-periodicity means that under the shift by the lattice vector, theta function is multiplied by a certain factor, explicit form of which is not essential at this moment. The factor space of H by natural action of integer 2G-dimensional symplectic group is the modular space of G-dimensional principally polarized abelian varieties. Such a variety is indecomposable if the zero divisor theta is irreducible. It is well known that on a smooth algebraic curve, algebraic is the same as compact complex one-dimensional curve. Of genus G, one can choose a basis of cycles in one-dimensional homology with the symplectic matrix of intersection. Choosing such a basis allows to introduce a basis in the space of holomorphic one-form, holomorphic differentials on the curve by normalizing their periods over half of the cycles. With this basis fixed, it defines period metric by taking periods of the same normalized differential over B cycles. It is known that B is symmetric and has positive defined imaginary part. As such, it defines the principal polarized abelian variety called the Jacobian of the curve. It is known that this Jacobian is indecomposable. The correspondence I just defined from the curve to the H space, upper Siegel upper half space, depends on the choice of the symplectic basis. But the composition of M of maps from the modular space of curves to H and then projection to the space of principally polarized abelian varieties is well defined and is independent of the choice of the basis. This map is called Jacobi Map and it is injective. It's a famous Tarelli theorem. The Riemann-Schottky problem is the problem of characterizing the image of Jacobi Map, Jacobi locus. Loosely speaking, it's about finding all relations between periods of holomorphic differentials on an algebraic curve. For 2 and 3, for G equals 2 and 3, the dimensions of two spaces coincide. So the closure of Jacobi locus is the modular space of principally polarized abelian varieties for such G by Tarelli theory. The first non-trivial case is G equals 4. In this case, Jacobi locus of codimension 1. A non-trivial relation was obtained by Schottky in 1888, giving at least local solution to the Riemann-Schottky problem. Local, I mean the following. The relation is very highly non-trivial. The locus it defines might consist of several components. Local means that one of the components is the locus of Jacobian, but there might be different other ones. The irreducibility of the locus of Schottky relation was proved only in 1981, establishing the first answer to the Riemann-Schottky problem in a trivial case. For G bigger than 4, Schottky relations, generalization of the Schottky relation, conjectured by Schottky and his student Jung in 1909, were proved by Farkas and Rauch in 1970. In 1984, Van Gaiman proved that the Schottky-Jung relation give a local solution of the Riemann-Schottky problem. They do not give global solution since the variety they defined has extra component already for G equal 5. That was shown by Donat. I gave all these dates for the only purpose, just to stress how hard the problem is and how slow the progress was made from one step to another, 100 years, 10 years, 20 years. Over more than 130 years of history, quite a few geometrical characterizations of Jacobians have been found. None of them provides an explicit finite system of equations. The first effective solution of the Riemann-Schottky problem was obtained by Shorter in 1986, who proved the famous Novikov conjecture. A matrix B is the period matrix if and only if there exist vectors u, v, and w such that the function u given by this explicit formula is the solution of the Kadamsev-Petriashvili equation derived in 1970 in plasma physics. Let me share with you my personal recollection about the moment the conjecture was born. Fresh PhD, I came to my advisor Novikov, very proud of myself, to show him this formula, how nice it is. And got a kind of cold shower. Novikov asked me, is it a formula or what? Is it just a symbol? Because if it is a simple formula, you should be able to check it by direct substitution. Maybe U is a solution to Kadamsev-Petriashvili equation for any B. If it's not simple formula, but good ones, it should speak for itself and define all parameters involved in this formula. And parameters involved are three vectors and the matrix. That was the moment when the conjecture was born. Indeed, substitution of U into the equation gives non-trivial system of equations in terms of level 2 theta function with characteristic and its derivatives evaluated at z equal 0. For quite some time, it was thought that the Novikov's conjecture is the strongest possible characterization of Jacobianism within the reach of soliton theory. It turns out not. There is a stronger characterization suggested by Walters. Actually, he also didn't make a conjecture. He asked the question, is it sufficient for the X to be a Jacobian if its Kummer variety has a trisecant line? The Kummer variety is the image of the Kummer map defined by level 2 theta functions as homogeneous coordinates. So it's a map from the abelian variety to the projective space of huge dimension. A trisecant is a line intersecting Kummer variety, the image of X under the Kummer map, in 3 points. Of course, in general, you don't expect that such a line does exist. Indeed, you take 2 points, draw a line, the dimension is huge, so too much freedom to avoid intersecting the line at the 3rd point. Nevertheless, it was known, it was a remarkable Fay discovery, that if X is the Jacobian, then K of X has, in fact, 4 parametric families of trisecants. Gunning proved that under certain non-degenerate conditions, the existence of 1 parametric family of trisecants characterizes the Jacobians. Mumford remarked that a certain degeneration of the Fay trisecant give the above presented formula of solutions of the KP equation, connected the theory of seconds with the theory of integrable systems. In fact, there are 3 particular cases of the Walters conjecture, corresponding to 3 possible configurations of the intersection points. All 3 points coincide. This is the degenerate case Mumford discussed. This is the case when 3 intersection points come together, so there is a point, inflectionary point at which tangent to the Kummer variety is tangent up to the order 2. In terms of the seconds, Novikov's conjecture is equivalent to the statement that X is the Jacobian if its Kummer variety admits the second order germ of an inflectionary tangent. So a tiny piece of a curve. It's weaker than requiring just one inflectional point. Two other cases, two other type of configuration. 2 points coincide, and finally, all 3 points, intersecting points, are distinct. Of course, the first 2 cases can be regarded as degeneration of the general one. However, when the existence of only one trisecond is assumed, all 3 cases are independent and require its own approach. The author proofs of 3 particular cases of the Welter's conjecture were based on a series of 3 fundamental equations of the theory of integrable systems. The Kadamtsev-Petryashvili equation, we already saw, 2-dimensional Toda equation, bilinear discrete Hirota equation. Don't look too carefully on this equation. The explicit form is not essential for my purposes. Whenever I will speak about equation, I will speak about them in general, not referring to any particular one. I want to give a picture what integrability of soliton equation means without referring to any particular example. Recently, algebraic-geometrical proof of the first 2 cases of the Welter's conjecture was obtained by Arborello, Cadoni, and Pareschi. Okay. Before I go to theory of integrable systems and how it is used in the proof of Welter's conjecture, let me mention the other result. The problem of characterization of p-varieties. As I said, this problem is almost as famous as Riemann shortly, but is much harder. An involution of a smooth algebraic curve naturally determines the involution of its Jacobian. The odd space with respect to this involution is the sum of an abelian subvariety of lower dimension, called the prime variety, and a finite group. The prime variety is principally polarized in a natural way if sigma has at most 2 fixed points. The problem of characterizing the locus of prime varieties into AG has attracted considerable interest. Analogs of many results weighted for Jacobians were obtained for the principally polarized prime varieties. The existence of family of quadrisecond. Quadrisecond is a projective plane intersecting Kummer variety at 4 points. The existence of families was proved by Fay, by Will, jointly with the bar. Analog of Ganin's characterization was for prime varieties was proved by the bar. I would like to stress that there was no analog of Welter's conjecture because Will and the bar constructed an example of not prime variety possessing 1 quadrisecond. The first answer on the characterization of prime varieties was obtained in our joint work with Sam Grushevsky, when we prove that, okay, 1 quadrisecond is not sufficient to characterize primes. It turns out you need 2. 2 symmetric quadrisecond characterizes prime. This is the explicit, this is the explicit statement. I will not present it here. I would like to stress that the proof of this statement requires constructing and developing the theory of new integrable equation, discrete analog of the Novikov-Veselov system. Okay, now about the second player of the game, integrable systems. A list of equations describing diverse nonlinear phenomena in physics to which the method of modern theory of integrable systems are applicable in numerous. It includes Korteweg-de-Vries equation, nonlinear Schrödinger equation, Sine-Gordon equation, periodic Toda lattice, and much, much more. It was, okay. There would be no place on my screen to put them all together. again, as I said, I want to speak about them as a whole, not about something particular, because they are 2D verbs. The last one here is a finite dimensional system. The first three examples are evolution equation on a space of functions of one space type variable. Three previous examples I already shown are two-dimensional systems. Actually, two-dimensional systems are the hardest part. The hardest and the most fundamental, because in one or other way, all other one-dimensional, zero-dimensional, integrable maps can be seen as certain reductions of two-dimensional systems. And these systems are essential for the purpose of my talk. So what's the most universal definition of integrable systems? The definition which put in the same framework all examples I have shown and not shown to you. The most universal definition is that integrable system is the compatibility condition of overdetermined system of linear. Example, the KP equation by itself is a compatibility condition of the system of two linear equations with L2 and L3 involving U, if it has enough common solution, two operators commute, and you immediately derive that U must be a solution of the Adams-Petriashvili equation. Of course, it's a loose definition. Maybe because of that, my colleague, my younger colleague, remarkable mathematician, complained several times. The theory of integrable systems is not a theory, it's an art. Too many different things are involved, and there is no common framework for all of them. Let me try to present this theory in more structured way, at least part of it. So, what's common for all integrable equations? First of all, each equation comes as a family of equations called hierarchy. So we're talking not about KP equation, we're talking about KP hierarchy, 2D total hierarchy, bilinear discrete Hirota equation hierarchy. The hierarchy can be seen as a set of commuting flows on a certain phase space. The space of certain linear operators, L of Z, depending on the spectral parameter. I will stress the importance of the spectral parameter a bit later. Flows are defined by the Lax equation, which possess a remarkable self-consistency property. The condition that the right-hand side of the Lax equation is a vector tangent to the space of operators. In other words, the equation is well defined as a dynamical system. So this condition defines A as a function of L, making the equation closed system. AFL is defined up to a certain choices. Different choices correspond to different flows, which easy to show commute with each other. Let me show the importance of the notion of spectral parameter on the simplest example of finite dimensional systems, because the presence of this spectral parameter, complex parameter, makes the connection. This is actually the place where two theories meet each other, algebraic geometry and spectral theory of linear operators. Example, let L be a matrix values rational function with certain number of poles of order 1. You increase the number of poles, you increase the order of poles, you get different integrable systems. But it's a typical example. For each operator, depending on the Z, one can define the spectral curve, which is defined by characteristic equation of L of Z. So for operators depending on Z, Spectral curve is what replaces the notion of eigenvalue for linear operator we know from our early days in college, at school. For generic U, the curve is smooth, and the normalized eigenvector is a meromorphic function. Normalized means the following. Eigenvector of a matrix depends on, is defined up to scaling. So you can normalize it, making the first coordinate to be 1, sum of all coordinates equals 1. The choice of normalization is not essential. So the basic statement that the correspondence that assigned to L of Z modular common conjugation, the spectral curve and equivalence class of divars of poles of common of eigen vector, which is a point of the Jacobian, is one-to-one on an open sets. This is called the direct and inverse spectral transform. Again, here in the theory of linear operators, we see the emergence of algebraic geometry curves. The basic fact is that under the Lax evolution, whatever it is, which A you choose, the curve remains fixed. So it produces, or better to say, the coefficients of the characteristic polynomials are integrals of motion for all Lax equations. The evolution is non-trivial for the divars, for the point of the Jacobian, but again, by some very basic principle, the evolution is linear. Example, another example more related to my purpose of my talk. The KP hierarchy. There are several definitions of KP hierarchy. We'll need two of them. The first one is due to Sartre, and it is identifying the phase space with a space of sequences of function of one variable, which is identifying with the space of pseudo-differential operators. So UI is the corresponding coefficient of the pseudo-differential operator L, which is just Laurent series in inverse powers of the derivative. The flows are defined by the Lax equation, where L, A, N, the second Lax operator, is a differential part of the pseudo-differential operator, which is a power of L. So this is the definition. It's not what one would like to expect. The phase space infinite sequence of function of one variable. When we speak about two-dimensional system, you would like to see it as a dynamical system on a space of Cauchy data for two-dimensional system, on the space of function of two variables. Such hierarchy was introduced in our work with Fong under the assumption that U is periodic. So we consider U to be a potential of the heat operator, assuming that U is periodic in X. The key step making possible to define the hierarchy as a flow on such a space is the following observation. Under the periodicity assumption, the equation L psi has a unique up to xy independent factor, wave solution. Wave solution is a solution of such a form. The first factor, exponential term, is easy predict from the type of leading terms of the differential operator, and that similar can be done for any two-dimensional operator. Treating U as perturbation, you get a solution with corrections. The problem is there are too many of them, and you cannot fix them uniquely. We say the normalization problem is find a translationally invariant normalization of the wave solution, which makes it unique. So in periodic case, it turns out that periodicity of psi, the coefficients of the wave solution, are defined this is the condition that fixes wave solution uniquely. As soon as the solution is fixed, you can embed in the previous form, Sata form of the KP equation by assigning to you a pseudo-differential operator L such that psi is an eigenvalue, eigenvector for this L, with K being an eigenvalue. And then you define the flows by the same formula, which explicitly written in terms of U has the form. So this is the floors, again, I stress, defined on the space of functions of two variables, space of Cauchy data or Kadamsev-Petriashvili equation. Okay, explicitly in the both cases, KP examples above, there is no spectral parameter. But in the second case, the case of periodic KP hierarchy, it is present in a Latin form under the double periodicity assumption. Double periodicity means that to define first of all periodic KP, we require that U be periodic in X. But now suppose it's periodic problem, fully periodic. So U is periodic in both variables. Then L operator, I put sigma, a complex number in front for purpose, seen in a minute. Actually, it can be seen as a family of operators depending on parameters. Namely, we can define, first of all, this space, which is an invariant under action of L if U is periodic. This is a space of sections of a line bundle of the torus or functions with the following monodromy properties. And then restrict L onto this space. It's going to be operator depending on W1 and W2 parameters of the line bundles. Then we can define in a similar way as before the spectral curve, Bloch-Floquet locus, by taking characteristic equation. This locus, the locus values of W1 and W2 for which there exists a solution L psi equals 0, which is double, or which is quasi-periodic in X and Y. By the same basic arguments, Bloch-Floquet locus, if exists, is time independent under Laplace flows, integral if exists, because unlike the previous case and the case of one-dimensional operators, where the corresponding quantity always exists, which might be not, for which the determinant might not be well defined. It turns out if sigma, the quantity, the complex number I put in front of the derivative in Y, is not pure imaginary and U is analytic, the locus, Bloch-Floquet locus, does exist. Abstract existence theory was proved by Taiman, effective construction in my work. For generic U, it is a smooth analytic surface of infinite genus. Non-existence of Bloch-Floquet locus for sigma equals I is an incarnation on maybe the most fundamental open problem in the theory of integrable systems. Is the periodic KP1 equation integral? KP1 and KP2 equations are two real forms of the KP equation. They both describe physical media with different properties, but they're real. In opinion of many experts, me included, KP1 periodic problem is not integral, but exact meaning of these words is missing. So right now, we have this verse only following. All methods used for the proof integrability of all other models fail for KP1 equation. It has a lot of exact solution, more or less the same amount as for KP2. But if, in case of KP2 equation, their closure is all periodic solutions, what's the closure of exact solution for KP1 it's a mystery. Okay, now I'm going to change a gear, and it often happens with integrable systems. The moment you set up a problem and find a reasonable answer, it turns out that you need to extend it. So I need to go beyond pure periodic problems for KP and other equations, because often I just try to stress that only in this case you can set up a reasonable Cauchy type problem for the equation. The essence is that there are too many interesting solutions for the same equation which do not fit in very rigid boundaries. All solutions, all integrable equations possess a family of algebraic geometrical solutions that can be explicitly written in terms of the Riemann theta function. They are not periodic, they are quasi-periodic. And for quasi-periodic functions, we don't know the right setting of the Cauchy type problem. But each solution for physical system is interesting for itself. So let me just speak about algebraic geometrical solutions to integrable systems. First of all solutions of finite dimensional integrable system are algebraic geometrical. So all solutions in all system you can get in the framework of the first example, they are all algebraic geometrical, and they can be solved in terms of theta function. The reason is the language of Baker-Heezer function, which is coming. For 1- and 2-dimensional systems, algebraic geometrical solutions are those whose orbits of hierarchy are finite dimension. That you can see as a definition. What are algebraic geometrical solutions? You have a hierarchy, infinite hierarchy for 1- and 2-dimensional system. But if the orbit is finite dimensional, this is algebraic geometry. That was the initial definition of the corresponding finite gap class of solution of KdV equation in a pioneering work of Novikov, which was followed by the remarkable works by Dubrovin, Matveyev, East, Lux, Makin, Van Merwijk, and Marchenko. Please excuse those. I ask excuse from those who are not listed here. The list is huge. It was the beginning of algebraic geometrical integration theory. So what are, and we will need it, what are finite dimensional orbits of the KP hierarchy? They are ultimately related to the theory of commutative rings of ordinary differential operators. The case of 2D to the bilinear discrete Hirota equation, you replace word of differential by difference. So the orbit of the KP hierarchy is finite dimensional when for all but a finite number of n, there exists a linear combination of generators of flows such that all of them commute with each other. This is linear combination which makes evolution flow stationary. There is no evolution along this, the corresponding relation. Preparing this talk, I just noticed that this year is 100th anniversary of remarkable work by Borknall and Chaundi, who prove the basic fact that if you have two commuting operators, they're related with each other through some algebraic relation. And this relation is given by the characteristic polynomial of the one operator restricted to the space of solution of the other operator. So Lm(y) equals Zy is an ordinary differential equation, defines finite dimensional linear space. You take characteristic polynomial, you get the curve. So ultimately, finite dimensional orbits of the KP hierarchy are related to algebraic curves. And that would be our final destination in proving Welter's conjecture. We're going to prove that certain orbits of the KP hierarchy, I'm not citing the two other examples, is finite dimensional. So complete classification of commuting differential operators for so-called rank 1, namely when the ring contains a pair of operators of co-prime order. This result of Brooks, Borgnal, Chaundi, my own Brooks, and the final touch, master touch, was done by Mapford, who give a remarkable formulation for the case when the corresponding algebraic curve is singular. I'm not presenting it here because in the application to Welter's conjecture, the curve is smooth. The full classification for arbitrary rank of commuting operators, this was my result. The commuting difference operators, theory of commuting difference operator needed for the 2D Tolaka lattice case, for the second and third cases of Welter's conjecture, was proved with different level of efficiency in Marburg and Map. So, how finite dimensional orbits or finite dimensional algebraic geometrical solutions of all integrable systems are constructed? The basic construction goes through definition of the Baker-Heezer function. The Baker-Heezer function is a function of an external set of parameters and a point of an auxiliary algebraic curve. For each set of the parameters, it is defined by the following analytic properties. Suppose gamma is non-singular algebraic curve of genus G with n marked points and fixed local coordinates in the neighborhood of marked points. Then for any set of G points in general position, there exists a unique function psi such that as a function of the variable p on gamma, it is meromorphic everywhere except at the marked point, has at most simple poles at the points gammas, if all of them are distinct, and this is the essential point, it has essential singularity in the marked point, but of very particular form, exponential singularity times pole or zero of certain order. These two conditions define psi uniquely up to p independent factor, which can be normalized. So the Baker-Heezer function is a generalization to the case of algebraic curve of usual class of exponential functions times rational function. The later are, as we know, are solutions to an infinite number of linear equations with constant coefficient. The same is true for the Baker-Heezer function. Namely, it is a common solution to a linear equations, but now algebraic curve plays the role of perturbation. Instead of operator with constant coefficient, you get non-trivial coefficients. The compatibility condition of all these linear systems, I'm not going to read them, it's not important, is a universal soliton hierarchy in Zakharov-Shabbat form. You take n equals 1, you get Kp. You take n equals 2, you get 2d toda. N equals 3 by linear discrete Hirota equation. The explicit theta functional formula for solutions are corollaries of the following explicit formula for the Baker-Heezer function. Again, reading it is senseless. All I want you to remember after the talk, that psi has an explicit theta functional expression that proved by hands. Uniqueness, well-defined, psi is well-defined as a function of p. It has needed singularity. It has poles. And so all solutions you can get from Baker-Heezer function are explicitly expressible in terms of theta function because they express through coefficient of the expansion of theta function at marked point. You expand this function and you get the explicit theta functional formula. Just an example of this, and it's time to go and review key points of the proof of Welter's conjecture. I'll stay in the first flex case. The others, with some modification, are following the same line. So there are three equivalent characterizations of the Jacobian. First, the equation with u given by this formula and psi by this formula, which you just saw a slide ago as expression for Baker-Heezer function. So this equation holds for arbitrary vector z. By addition formula for theta function, the result of substitution p, psi, and u into the equation leads to the equation for the derivatives of Kummer map at certain points, which says exactly that point A over 2 is an inflection point. So the first equality for some fixed A is equivalent to the existence of inflection point. We know that actually if it's Jacobian, then A, P, and E are not just one constant. There are one parametric family of such solution parameterized by the curve. So we need to prove the Welter's conjecture. We need to show that if for one A it is the equation holds, it holds for one parametric family. This is our goal. How we prove it? We prove it through the, don't be afraid, from the third equivalent characterization of the Jacobian, ugly looking equation valid for theta function and its derivative along the theta divisor. To explain you why and make these relations transparent, I would like to, and this is the working tool through this equation, the Welter's conjecture is proven, not through trisecond condition. So what is this equation? I need to introduce, to explain this equation, a notion, a new, very nice notion, I like it very much, monodromy-free linear equations. Three main examples are one out of two auxiliary linear problems for the KP2D Tode and bilinear discrete equations. They're all written here. I will use the first of them. Two others are difference functional equation. In all of them, the coefficient of the equation, under the assumption that tau is entire function, are meromorphic function. So let's ask a very simple question. When equation with meromorphic coefficients has meromorphic solutions, very naive question. Remarkably, it turns out that the answer is very interesting and non-trivial. And it was a kind of mystery for me when we found the answer in our joint work with Arbarella and Marini. So, example, let psi be a meromorphic solution of the equation. You take u and psi expanded at the zero, simple zero of tau function, plug into the equation. You get an infinite set of equation mixing up coefficient of expansion of alpha, of psi and u. Then take derivative of the first equation and use the other two. And the equation decouples. You get the equation that the second derivative of the zero with respect to the second variable is equal up to factor to the coefficient of Lorentz expansion for u at in front of the first order term here. We call them, for the reason you will see in a minute, meromorphic Calogero-Moser equations. Formally, if we represent tau as an infinite product, then the equation for its zeros have the form, which is in the case when tau is a rational trigonometric or elliptic polynomial, coincide with the equation of motion for rational trigonometric or elliptic Calogero-Moser systems. Recall that elliptic Calogero-Moser system with n particle is Hamiltonian system with coordinates Q and P with canonical Poisson brackets with Hamiltonian. The corresponding equation of motion admits the Lax representation, whose entries are given here. They depend on the spectral parameter, which is a point of the elliptic curve. And as such, they can be, the equation of motion can be linearized via the spectral transform. This is the form of algebraic answer for the solution of equation of motion of elliptic Calogero-Moser system. There is no spectral parameter in the monodromy free setting. Remarkably, the equation for zeros we got are sufficient for the statement that if you have one meromorphic solution, you have infinite number of them. Namely, if you take, suppose the equation for zeros of tau holds, then the wave solution we already saw of the equation are meromorphic function. It is surprising fact because on each step you are solving differential equation for the coefficient of the wave solution. And in order to be the solution to be meromorphic, the residues of the right-hand side iteratively should vanish. So infinite number of the condition, just one relation we derive is sufficient to satisfy all of them. The same is if you did for two other examples, will lead you to annals of Rosenau-Schneider's model, beta-ansatz equation. Let me skip it. So let's summarize. The monodromy free property of linear equation with meromorphic coefficient leads to equation on poles. Implied that wave solutions are meromorphic. So having one solution, we have a family, formal family, but after some work, we'll see that it's actually a family. And this is where we're leading to the solution of Welter conjecture. In the cases when there is a normalization which defines the wave solution uniquely, the monodromy free property is invariant under the flows of the corresponding hierarchy. Is the orbit finite dimension? Okay. In the most general form, when the answer for all this question is positive, so the equation are not formal but well defined, the normalization problem has a solution. So on the space of such function, there is an action of the corresponding hierarchy. In the class of abelian function, the class we introduced in our joint works with Schroeder, particular case of which are the case when of interest, namely, the abelian function is a function of the form tau, which is a function of n-dimensional argument restricted to a line ux plus z. And tau as a function of z is a holomorphic section of a line bundle on an abelian variety. So under the shift by lattice vector, it is multiplied by a certain factor. It turns out that the equation for zeros of tau really, because zeros of tau corresponds to points where the line ux plus z intersects the divisor of tau function. So the equations for zeros becomes equation valid on the tau divisor. It's tempting to call them abelian collinear model, Rosenau, Schneider, and nested beta and zeta equation. If you remember the frightening formula in characterization C, this is how looks the abelian collinear Moser system. Nested beta and zeta is much simpler and nicer. So the answer is positive. So all algebraic abelian solutions correspond to monadromy free properties. The orbit of the corresponding hierarchy is finite dimension. So they are algebraic integrable in a sense I explained from the beginning. So for GNF, so the final answer is the classification of such solution, that all of them, tau function, are obtained by restricting theta function onto the image of a fine embedding of x into the Jacobian of the corresponding curve. A linearization on gamma of nonlinear dynamics for tau indicates the possibility of the existence of integrable system on spaces of theta functions of higher level. The case n equals 1, which leads to remarkable elliptic integral system, is an example. Does this theory exist or not? The time will show us. So, in remaining 3 minutes, I left with the pleasure to present the most recent result on characterization of Jacobians with involution, of curves with involution. It seems that in full generality, this problem has never been considered in algebraic geometry. At least the author is not aware of such. This problem arises from the attempt to construct solution and classify them for various integrable hierarchies with symmetry, CKP, BKP, various symmetries in Toda, also sigma models. The answer is that the curve of the x is the Jacobian of curves with involution. First of all, if it possesses a flex, this we know, this is characterized as Jacobian. What singles out of them curves with involution is the condition that image of the Kummer map of the prime variety is a kind of flat. It lies in the hyperplane orthogonal to explicitly given vector. It's a, as far as I know, it's a new concept, in some extent orthogonal to a notion of seconds. How useful it's in algebraic geometry, we'll see in years to come. I have 1 minute left, and maybe just to show you a slide. I try to cover as much as I can, but what is left may be the most interesting part of integrable systems, algebraic geometrical methods in integrable systems. Hamiltonian theory of such systems, Witten perturbation theory and its connection with Frobenius manifolds, Seiberg-Witten solution, and various applications to the geometry of modular spaces. Okay, thank you.
Well, thank you very much, Igor, for this beautiful lecture and the wonderful results. Truly amazing. If people want to ask questions to Igor, please send them to him by email and he will gladly answer them. Thank you all very much.
Thank you, Carlos. Thank you.